The next set of the next topic, which is the last topic in segmentation that we are going to take, it is segmentation based on motion. So this is also very important. It has a lot of important application, especially in videos. So normally, visual motion is a very important cue which is used by people, by humans also, to identify which are objects, and especially to distinguish between moving objects and the background. So in video, for example, if you have a video of a traffic scenario, then based on objects which are moving like people and vehicles, they will be moving, and the road and other parts will be stationary. So based on which pixels are moving, basically it is very easy to identify um, foreground objects. For example, in this scenario itself, you can see the tree part can be easily identified from this sky part by seeing by if you can if you had, by seeing which pixels are actually changing, which pixels are basically moving. A motion can arise from two things. Your your camera may be stationary, but the objects may be moving, and that may lead to motion in the video. The other scenario can be the object may be stationary, but the camera itself may be moving. So camera itself may be placed on a moving platform. For example, if a camera is mounted on a drone or 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 a moving vehicle, then also there will be a relative displacement that will be seen in the video. So in this class, only going to focus on the scenario where objects are moving. We are not going to discuss when the scenario when the camera itself is moving. That adds one level of difficulty more, because then you'll have to do image registration to keep your background stationary. So we'll not talk about that here. So we will talk about simple stationary background, stationary camera scenario. And this thing is popularly known in computer vision as moving object segmentation, or sometimes it is also known as change detection. This thing that we are going to discuss, this technique is called change detection or moving object segmentation, and it is used mostly for segmenting out moving objects like vehicles, pedestrians in a video scenes of a visual world. It is normally the first step in doing automated video analysis of uh, dynamic videos. For example, a surveillance video. When we are doing a surveillance video, if you are doing surveillance, automated surveillance, there the first step before you can track objects and before you can recognize activities or events in the scenario, you will have to first segment out moving objects. Similarly, if you want to do traffic monitoring or if you want to do human action recognition, so before you recognize the action of a person is doing or people are doing, you need to first segment out their moving parts, their hands or their legs or their heads. So the moving parts have to be segmented out from the background. So normally that is the first step before you do the further analysis. So just for your information, this is a high level figure, which is basically uh, this intelligent video analysis is an important research area in computer vision, because as we know, it has a lot of applications, especially with a lot of surveillance cameras being installed everywhere in the city. This is a very important research problem: how to do intelligent video analysis, automated video analysis, automatically detect objects and track them. So this is the set of tasks that is done generally on input video. In the first step, we do the moving object segmentation, and optionally we do feature extraction. We may do extraction of features like shift or the other features which are useful. For doing this segmentation, normally we have to use a background model. We'll talk about this why we need a background model. But after segmentation, we basically do connected component labelings, and we get label blobs. So we can distinguish one moving object from another moving object, and then using the features we can classify them, those blobs, whether it is a vehicle, or it is a person, or it is animal, or some other things. And then based on classified objects, we may track objects which are of interest. Of a particular person we want to track, or a particular vehicle we want to track, we can do a tracking of that. And after tracking, we get the trajectory information, where are the points, where are the locations where they have actually moved. And based on the trajectories, we can do a further higher level analysis, trying to understand the activity or the event that is happening in that scene. And based on that recognition, there can be a decision taken by authorities about who are doing the surveillance or whatever. So this is a high level application, but we are only going to talk about the first step, segmentation, in this class. Later on, we may talk a little bit about tracking. I'm not sure whether we'll discuss a lot about it, but a little bit we can discuss. So the thing that we are going to discuss is how to segment out moving objects from background. And this task is popularly known by the term background subtraction, because what we are going to do is basically we would like to subtract out background from the given video scene in order to get the moving foreground region. So we are given a video frame from a static camera observing a scene. Our goal is to separate the moving foreground objects. So what we are calling foreground is the moving part, and what we are calling background is the static part, the part of the scene that does not change position with time. That is our background. For example, in this case, this person may be doing some gesture, maybe moving around, but all the remaining part of the room will remain static, should remain static if it is an indoor scene. So the goal of our task is to be able to segment out this moving person from this remaining background. Similarly, in this traffic scenario, these vehicles are moving part of the scene, and other part of the scene, which is the road part and the traffic lights and the buildings, they are stationary part. So the goal is to basically segment out the regions which correspond to the vehicles here, and all of the parts should be considered as the background, because that is the static part that should not change position with time. And to discuss this, how we do it. So from now onwards, we will consider, because we are taking now we are not just considering a single static image frame. We are considering an entire video, which is a sequence of frames captured over time. So there is a third dimension that is coming now in our case, which is time. Till now we were only considering in space, a 2D space, X and Y. Now, because we will have a sequence of frames over time, so every pixel or everything that we are going to, our image data is now a function of three things. It is a function of X, Y in space, and time. So that's why I'm writing our image data as a function of X, Y, and T. So the approach is very simple. The basic idea is very simple. How to obtain, if you want to separate out these moving objects, the simplest thing is at a given point of time, take the image frame at that particular time, and if you somehow have a reference frame, which is the background, which you consider your background at particular time t. So somehow if you get this reference frame where you don't have which is basically the image of the static part of the scene. So this, as you can see here, this image only contains the static part of this scene. So to segment out these moving objects is simply, if you do simple image subtraction, this image, this I minus this B, then these locations will only have a different than all other locations. So In the difference image, you will have only non-zero values at these locations, and all other values you may have either zero or close to zero value. And then you basically apply a threshold. So the steps is basically you somehow obtain the reference frame, the background frame for time t, subtract that estimated background frame from the input frame, then apply a threshold to the absolute difference. Normally we take the absolute difference because whether this is higher or this is lower than this, we are interested in change detection. Whether changes towards the higher side or towards the lower side doesn't matter. So we will take the absolute difference and then apply a threshold. So wherever the difference is greater than this threshold, those regions will correspond our foreground region. So this is the basic idea of background subtraction. This is the steps this is the basic idea of background subtraction. But the crucial part here is how to estimate this background at time t. This is the crucial part which makes it difficult. How can we estimate the background at time t? Why it is difficult? We actually need to have a model of the background, because there are several factors which can cause your background to change. You can say, okay, simplest thing is if you take a video when there is no object moving on the road, take that image frame itself as a background image. But it may not that will not suffice over a long period of time, because after some time the illumination in this region may change. For example, this image may be an early morning image where there were nobody moving on the scene, but during daytime, during afternoon, the overall illumination this scene itself will change, or there may be some difference may have come, or different. For example, if you see this car has been parked now here, which was not there earlier. So some things which were parked earlier may not be parked, may move out from that scene, or a new car may come and get parked at this location. Or there may be a wind motion, because of which there may be flag which may be moving, or there may be trees which may be moving. So there are several factors which can cause changes, which may cause the background to change. There may be illumination changes. There may be natural wind motions which can cause some portions of the background to move. For example, if there is a flag, or if there are leaves or vegetation in the background, they may move. There may be shadows also due to overhead sun. There may be shadows of moving of objects. There may be flicker. There may be flicker in the scene, and moving object itself may halt sometime and they may become stationary, or something which was parked now it starts moving. So these are the different changes, environmental changes as well as practical changes that may happen in the scene, which may cause your background image to keep on changing. So we need to keep on updating our background, and to keep on updating our background, we need to have some kind of a modeling which can keep our background up to date. And we using that updated background, we should do this subtraction thing. So this is the overall pipeline or the processing that we will be doing in order to get our foreground regions. We'll take the current frame using our background model. We'll have some method to maintain our background model. So with that, we'll get an estimated background at time instant t. We'll take the current input frame at time t. We'll get the background at time t from our background modeling. Then we'll do the subtraction background. Now in the and then we'll apply the threshold. Now in the thresholded image, there may be, as I said, there may be some small noise regions, there may be some clutters, or some regions they may be broken. So we may have to do some morphological processing to remove small noise regions and to join regions which were disconnected. We'll see example of that later. And after doing that post-processing, we can do connected component labeling algorithms to label our blobs, and those will give us different foreground blobs. And we need to have a feedback loop to update our background model. So we need to keep on updating our background model with the new frame that we have seen. We should keep on updating the background, because background need not non cannot be static. It has to be constantly updated, unless it is an indoor scenario where you have a fixed lighting and there is nothing moving in the background. In that scenario, you can always take a reference frame where the object is not there, and then use that reference frame. I have taken a test video on, it was available on the internet. Of course, it's a very difficult test video. As you can see, it's an outdoor video where there's a lot of background movement due to wind motion. There are flags swirling, there are things moving, there are shadows of objects, moving objects. Objects are of different size, there are people, there are cars, they are moving at different speed. There is a specular reflection on the sun on the window shields and so on. So it's a very difficult scenario, and to get an ideal output, you need a very advanced techniques to get a good output. But we'll discuss some simple techniques and one advanced techniques for seeing how they perform on this test video. So the simplest technique is called basically frame differencing, where the background is nothing but is taken, but the image frame at the previous time instant. So background is taken to be the previous frame. So that means if this is the background at the previous frame, this is the current frame, you just subtract the current frame from the previous frame and then do the thresholding. Why we are taking previous frame? Because the idea is that our whatever the changes has happened, it would have reflected in the previous time instant. So when we say previous time instant, it may not be just the exactly -1. It can be t -5 or whatever. You can some t -k. So normally a video has 30 frames per second. So you would like to have the previous time instant that you want to consider is, let us say, 0.5 second before, or maybe 0.25 second before. So in that case, the number of frames accordingly you can calculate. It can be 15 frames before or 10 frames before or whatever. So accordingly you can subtract, you can get the previous frame time and let's subtract from that. So the thing is, the object which are moving would have displayed slightly from the previous location. So in the previous frame they would be a different location, and the new location they would be a different location, and all other part which has not moved, that would have been stationary, and the illumination will not change so much within that 0.5 second or 0.25 seconds, and all other changes may not happen so much. Only the objects which are constantly moving, they will have only changed their position slightly. So I'll show the result on the test. Let's show the result. So if you do this thresholding, if you do this frame differencing on our test video, you get this kind of an output. So if you can see it is amazingly, it is able to take care of this background motion of these trees which are moving so fast, and it is detecting many of the moving objects, these peoples and these cars. But one thing, if you can see, for example, if you see this car, not entire car has been detected. So this part has been detected, the back part of this car has been detected, but this part, if you see this region is entire black. Probably this car itself was black, and no, that may not be the reason. The reason why, because this size of this car is large, and it is this entire body has probably a uniform color, and the shift, it may have within the two time frames, it may have shifted only little bit. So at these locations, probably because the pixel have been shifted little bit, but both these pixels are belong to the same body of the car, which has the same intensity. So even when you do the differencing comes out close to zero. So this interior of this object is not detected. Only the boundary of the object has been detected. Same thing, if you see, it will be for small objects you can detect more things, but for large objects you can see the entire object is not detected. For people, you can see more portion of the people is detected than the vehicles and so on. It's not a great thing, but it has good advantage. The computation load is almost nil, because you don't want to do any modeling. You are just picking up the previous frame, and the model is highly adaptive. So any change that has happened, it gets quickly reflected. If the background has changed even slightly, it will get quickly reflected in our background model. So it is highly adaptive with respect to time. But the flaws, as we have discussed, for objects, large size object with uniformly distributed intensity values, the interior pixels get interpreted as a part of the background. For example, interior part of the vehicles, they were not detected as moving regions. An object must be continuously moving, otherwise it becomes part of the background. So if an object halts for even a 0.5 second or whatever the time instant that you're taking, if an object halts for even a short moment of time, it may not get detected for that time instant. So it has to be continuously moving. And another important challenge with this method is how do you decide the threshold value? Because, for example, if you set like threshold value, a low threshold value, let us say 25 on the traffic scenario, then you get a lot of irrelevant noise regions. If you increase the threshold, you can get rid of some of those noise clutter regions. But if you go beyond, then the problem is, as you can see, the object regions get broken, because some of the interior parts, they get not detected as a background. So you get broken objects. And if you increase very high, then you miss altogether the entire object itself. So maybe a good threshold could be this one, or maybe even this one. Because you can remove these noise regions by post-processing. You can do morphological erosion to get rid of these things, and you can do morphological dilations to close these object regions and get us one object in this for all this entire thing. That's why we'll see morphological processing is normally followed as a post-processing to improve the segmentation results. But how do you set this threshold value? If you don't know the scenario, you have to set it by experimentation only, and it will depend. The accuracy will depend a lot on how fast they are moving, the frame rate per second, and the threshold value. A slight improvement that you can do, instead of just using the previous time instant frame, you can actually take a bunch of previous frames, and you can take a bunch of n frames, previous n frames, and then take an average of all those n frames. So take an average of all n frames in time. So this is not, the mean filter is not the same mean filter that we are talking when we would take average over in space. We'll take a mean average value in space. Here we are not talking about that. We are saying we take n frames, the previous n frames in time, and then do a pixel by pixel averaging in time. So that means averaging is done over corresponding pixels in the given area. Okay, so now your background estimation, the estimated background at time t is basically an average of past n frames, and use that as our background and subtract it from the current frame, and then do a threshold. So for example, for the same traffic scenario, if you take NS10, take an average of 10 images, then this is the estimated background that you get. As you can see, the vehicles which are moving, basically, because of taking an averaging, you have tried to, by doing an averaging, what you are basically trying to do, you're trying to estimate the pixel value is closer towards the background value, because the background is the static part, but the objects are moving. So that is the transient part. The object intensity values are the object intensity values are in flux. They are continuously moving, changing, but the background part is stationary. Background is static. So when you take an average, the changing the transitory part, which is continuously in flux, that has less impact than the static part. The static part, the intensity part, is the underlying intensity value, whereas the transitory part is continuously changing. So at a given point, this is always, the static part is always there, and the moving part is always changing. So when you take an average, the average comes more closer towards the static part, and tries to get rid of the intensity values of the moving part. So you can see it tries to, especially for smaller objects and you can see the average value has come closer towards the road value, and using that, when you subtract, you get this kind of an object result. It's not a great, for example, this, you get some kind of trailing factor here. So the object the image which was only just this much, you have got an image region this large. You can improve over it by increasing the number of background frames over which you do the averaging. So for example, instead of taking NS10, if you take NS50, then the estimation becomes more closer towards the static part. You can see this estimated background is slightly better than this estimated background, for the same reason, because now over a larger period, if you take an average, then for most at least for 25 frames, the object, the region will be the background region, and for 25 frames probably that region may be covered by an moving object. So you will get a more closer averaging towards the background region, and you can see the foreground result here is much better as the previous one. You can improve upon it slightly. Of course, there is some problem with this. You have to now store these 50 frames. You have to have a memory to store these 50 frames and keep on updating it. Or you can do a running average. You can do a running averaging. If you don't want to store these 50 frames, you have to do a running average method to keep on updating your frames. You can also improve the results instead of using mean if you go for median filter. So as we have seen in spatial case also, when we are trying to remove noise, median filter sometimes tend to perform better than mean filter, because mean filter would always distort the intensity value, whereas median filter would not distort the intensity value. It would get rid of outliers at the same time without changing the intensity value. Same thing, same logic can be applied here also. By you can actually take previous n frames and choose a mid, sort those pixel values, and then pick the middle one. Pick out the frame, the intensity value, which is the median value. So the advantage with this is that the transitory part, the flux part, will actually settle towards the higher side or the lower side. And if at least 50% of time, if your frame was uncovered, frame was not covered by your moving part, then 50% of your pixels will correspond to your actual background intensity value. So when you are picking up the median value, it will most probably be your background intensity value, and it would not be distorted by the effect of your foreground intensity values, as it would happen in case of taking an averaging. Averaging will always have some component of the foreground regions also, but median filter is better in the sense it doesn't get distorted, it doesn't distort the intensity values. So this is an example of estimated background using mean filter, and this is the result background result that you get after thresholding and subtracting with the median value. This is an example image, which sequence of image frames, where we show the results of using a mean and the median background. So these are some frames taken, some sequence of frames taken over time, and this is, so if you see this is a sequence of image frame where people are moving, and these are not, as you can see, the movement is substantial here, so these are not consecutive frames. Probably these are frames sampled at some distance, some time instant t. And the mean image, I think this is either the mean or the median image of this sequence of image. So you can see, for example, these people were probably they didn't move over from these locations. So in the mean and the median image, these people still form the part of the background. But all these people which were constantly moving, they do not come in the estimated background. They were actually cleared in the background. Again, go back to the sequence. You can see these people were moving little bit, but they did not change their position. So if you subtract this image, let us say, and this estimated background image, then you can see wherever there are the moving peoples of bicycles, there you have a non-zero difference, and all other locations you have a close to zero difference. And if you apply threshold over this, then you get this result. And then if you do morphological cleaning, you do morphological erosion, and then you can remove those noise regions, and then you can do dilation to regain the size of the moving objects. And these are your foreground regions. Some of them get joined, so now 2 or 3 people may get joined together because of doing this erosion and dilation and because of their close proximity. But still, at least you are able to identify the regions where there were people moving. These people who were sitting, but because they were doing some motion, they were either moving and they are doing some motion. That's why they have also been, those regions have also got detected in the output image. Now to do median filter, again, you have to do sorting. You have to store previous end frames and do sorting. But you can get rid of that by doing, just like you do a running average, you can also do an approximate median filter. You can do some approximation to avoid that memory and computation requirement. Basically, the idea is very simple. You take the current frame, and if the value is larger than the current background pixel, then you increment the background by 1. If it is less, then you decrement the background by 1. So over some time, it will eventually converge to an estimate which will be somewhere around the median, where half of the input pixels are greater than the background and half of them are less than the background. So these are called approximate median filter, approximate median algorithm. But it will depend, the convergence will depend on the frame rate and so on. Sometimes it is used. So the result of doing this mean or median filter. So this is the background model that you get on the previous test scenario. So you can see there is some effect of the moving regions. You can see there is some distortion in the things. So this is a background model that you get, updated background model at different time instant. And using this background model, this is the result that you get. Now you are not able to get rid of this highly dynamic motion of the background trees because this is not so highly adaptive as it was, as frame referencing was highly adaptive. But median filtering, because you are taking past 50 frames and you are slowly adapting, so you are not able to get rid of those things. But now you can see you are able to detect the entire object. I'll rerun it. Now you are able to detect the entire vehicle, unlike the frame differencing method where you are not able to detect the interior parts. You are able to detect. There's another problem. You can see the shadow, the ghost effect that you can see here. That can be removed if you increase the number of frames. If you increase the number of frames to larger, the buffer size, if you increase, this trailing effect can be got rid of. But at least the output is much better than the frame differencing, only with the exception of this highly dynamic motion of wind motion due to the vegetation. So these models are simple models, simple approaches. They give us good output, reasonable output. But there is still one shortcoming with this problem. Is how do you this threshold? How do you decide this threshold? And you have to do some heuristic. You have to do a trial and error to fix this value threshold. And the problem is this: now you are using this threshold as a global threshold. For every pixel location, you are using one single threshold value, which doesn't seems to be a good idea, because different regions changes may be happening differently according to the object type and its motion. So the threshold should be adaptive for different regions, for different portions of the image. Probably we should have different threshold for different regions rather than having a single threshold for the entire region. And there is even a bigger problem. This threshold is not a function of time. So even if you do trial and error, you fix a threshold value. Now that threshold value is same for every frame now onwards. So you cannot tweak it for different time instant. You cannot keep on changing this threshold value for each time frame. So ideally, as I said, if the background is getting updated over time, then this threshold should also should be a function of time. It should also change over time in order to get a better output. So we'll see some advanced techniques that get rid of these problems. I'll stop today's class session at this point. In the next session, we'll see some better techniques which takes care of these problems and get much better output.